Today I'm actually going to play the role of a salesman a little bit. And I didn't want to look too serious, so I went for a quick swim right before I gave the talk. So hopefully you shouldn't take this talk too seriously. Just a little bit of a sales pitch for OCaml. So real quick about me, I work at a company where we have a Clojure stack and an OCaml stack. So I kind of see both sides of, call it functional programming religions. So today I'll be a hype man. I'll go over some of the cool stuff that you can do with OCaml, what it allows for. But I will try to be semi-responsible and tell you some of the caveats. That said, there's only 30 minutes, so I'm going to leave a lot of nuance out. If you want to hear all the bad things about OCaml, please come up to me afterward. I'm happy to talk about how terrible it can be. And then the last thing is, this is kind of a thought experiment. I'm not saying necessarily that you should adopt OCaml today. But some of the stuff that you can do, it's interesting to try to figure out how would you pull those into other languages and other stacks. So kind of backing up, whenever I think about building apps, there are kind of several goals that come out of that. A big one for me personally is correctness. Tracking down bugs and making sure that there are no bugs, or as much as possible that there are no bugs, is very important for me. Being able to develop apps and deliver them very quickly is important. Performance. A nice thing to have is code reuse where possible. Security oftentimes does not get as near as much attention as it deserves, but it is a big thing. And then finally, maintainability. That said, like in reality, whenever it actually comes to delivering apps for clients or for our companies, that list is kind of ordered in a very, very different way. And it looks something like delivery speed, delivery speed, delivery speed. And then you have a few other things. And then down at the bottom, there's kind of like, and by the way, we want it to be correct, fast, and secure. And actually, I think this is OK in lots of ways. I mean, it kind of goes towards sustainability, where you have to deliver very, very quickly in order to try to invalidate any business hypothesis that you have. So it makes sense that we try to deliver as quickly as possible. But on the other hand, if you don't have those other pieces, the correctness, the ability to maintain code and reuse code and whatnot, you actually suffer on the developer and operation happiness. And if developers are not happy, it's not a very sustainable business long term. So try to find like a balance between there. And is that balance OCaml? Maybe, maybe not. We'll see. But real quick, raise your hand if you have ever used OCaml. OK, especially at university. And then keep your hand up if you enjoyed it. All right, a few people. All right, so very cool. I'm glad to see that. That's more than usual. All right, for those of you who don't know, OCaml describes itself as an industrial strength programming language supporting functional, imperative, and object-oriented styles. And that sounds like a terrible description as far as I'm concerned, especially the multi-paradigm thing. But we'll see how that helps a little bit later. Quick syntax, so you guys don't get scared. I mean, this is an OCaml example of the Fibonacci sequence and a Python example. I think we're roughly equivalent. It's not too bad from syntax difference. I think there's one extra token maybe in the OCaml version. So from a syntax point of view, there's actually not that much difference whenever you're writing OCaml, if you don't want it to be different than when you're writing Python. But structurally, you actually get a lot of very interesting properties out of it. So first of all, it has a very, very lightweight but incredibly thorough type system. So if we go back and we look at the code real quick, like there are no type annotations, right? There's no like this is a string and this returns this or whatever. Like OCaml generally just kind of figures it out for you. And you can go ahead and add type annotations whenever you want to be unambiguous or you want to enforce some things. But generally speaking, like you just kind of develop just like you would in Python. But you get all the benefits of a lovely, lovely type system that helps quite a bit. OCaml also has a crazy obsession with performance. It's actually kind of worrisome, the extents that they go to eke out even small bits of performance at times. It also is statically compiled. And this is kind of important for a lot of domains, where you want to have a very, very predictable characteristics. So we don't have to pay, for example, a JIT. And we don't have to worry about our code getting de-optimized because we hit some different path. You can basically take OCaml, look at the assembler output, and know exactly how it's going to run. That said, it actually has a very, very strong compile to JavaScript story. So you can take OCaml, you can compile it down to JavaScript, and you can use existing JavaScript libraries like React quite easily. And then on top of that, it actually compiles down to ARM64 as well. So this means some cool things like actually being able to reach out to mobile and have native mobile apps. So not necessarily running through a JIT, but actually running native ARM64 code. But also on Raspberry Pi and embedded devices. And then finally, it encourages a functional style, but it doesn't require it. So those of you who have kind of worked with Haskell might have found it very difficult to then get it to work with existing libraries that have an object-oriented approach. This is not necessarily a problem with OCaml nearly as much. And then just kind of historically, because of the way it's, where it sits, it's actually really, really well suited for system development. It's kind of been its bread and butter for a long period of time. But it's very high level and expressive enough where it actually works very well for app development as well. So to give you an example, Unikernels. How many of you guys have heard about Unikernels? Oh, very cool. All right, so real quick, it's a kind of a new way of building and deploying applications. It's an older idea, but it's only kind of recently become feasible for lots of reasons. Effectively, it's saying, like, what if we could have an operating system as a library? So right now, whenever we develop a application, say we develop a Node application, we write some JavaScript, we push it to a server, and then that's going to run on Node. Node itself is actually going to run on top of Linux usually, right? And we have this kind of just 50 million lines of C kernel that provides so much functionality. Like, it's incredible the amount of functionality that the Linux kernel actually gives you. But oftentimes, you don't need all of that functionality. But it is very difficult, even if you don't need it, to actually strip that out of the kernel. It's not a normal thing to actually slice up the kernel in Linux. So OCaml has done a very good job of kind of leading this Unikernel implementation, I think. There's a library called Mirage, which basically has been some pretty crazy people implementing very, very low-level libraries in pure OCaml. So things like the TCP IP stack, TLS, data storage, all the stuff that is usually taken care of in the kernel for you is actually taken care of in pure OCaml libraries in OCaml's Mirage. So then what you do is, whenever you're finished with your application, you compile it ahead of time, and you only pay for what you use. And the idea here is, we're going to, at compile time, we're actually going to pull in all of these pure OCaml libraries, and we're not going to actually use the Unix kernel at all, or the Linux kernel at all. We're actually going to create an entire VM that is just our application. So it has some pretty cool properties here. We're going to run our application directly on top of the hypervisor. In fact, your app is the entire VM. So you get some really, really cool small numbers from this. You get thousands or tens of thousands of type-safe and memory-safe code, rather than millions of lines of memory-unsafe code. And this has huge security implications. So again, I think security doesn't oftentimes get its due. But this is really important. If you think about a lot of the vulnerabilities in OpenSSL and in the Linux kernel, oftentimes it comes from memory-unsafe code. And it's not for lack of very smart people working on it. And it's not for lack of eyes looking at it. But it is really, really hard to actually write secure memory-unsafe code. And then not only that, but because you have far less code, there's much less surface area for vulnerabilities to kind of be stuck in. Whenever you actually compile your application and you create a VM, it's generally in about 100 kilobytes range. And this has kind of interesting implications for, it's so small that every time you deploy a new version to a server, you can literally check that into a Git repo. So you actually have this ability to go through and look at every single version that has ever been deployed. And now, if you hit an error in the server, you can literally say, what version of the server was that? And you can go and check that out, and you can rerun that and do an immediate repro case of that error. And not only that, but it's so small that it boots up in 50 milliseconds. So I've talked to some people here who have optimized, for example, Arch Linux, and they got it down to a couple hundred megabytes. And they're actually able to get a workable Linux machine booting within tens of seconds. And that's actually pretty good for a Linux machine. And generally speaking, whenever we develop and whenever we think about deploying, tens of seconds is not so bad. But things change dramatically whenever you have a 50 millisecond boot up. Right? This is orders of magnitude faster. It changes things in a way where you can actually start to experiment with different means of deployment. For example, there's this idea of Jitsu. So literally, let's say I have my Unikernel running at demo.whatever.com, and a client wants to access it. So the first thing they're going to do is make a DNS request. That DNS request comes in, and we have a custom DNS server written in OCaml sitting there. And before we actually reply to this with the address of the Unikernel, we're literally going to go and boot a new VM specifically for this one connection. And then, because it will boot in 50 milliseconds, that is shorter than the TCP reply window. So we can then say, when we boot, we can wait for it to boot, reply to the client and say, here's the IP. And then they do their dance. And then as soon as it's done, we kill it. So it's we basically can boot this thing up literally for every single connection that comes in, and then we kill it immediately. So you get these really cool things where now we're actually able to utilize our resources much, much more efficiently. So whereas beforehand we were able to run maybe hundreds of VMs on a server, we can actually run tens of thousands of them pretty easily now. So another cool deploy target for OCaml is JavaScript. So we can take that same code that we're working on in the Unikernel, and we can compile it down to very, very efficient JavaScript. OCaml's runtime model actually matches the JavaScript model quite well. And so with that code, we can actually share type definitions across the code between the server and the client. We can share modules between the server and the client. And pretty much any pure OCaml code will just work. For example, the TCP IP stack that I was talking about in the Unikernel that is implemented in pure OCaml, that actually compiles down to JavaScript, and you can run that in the browser. And this is not necessarily something that jumps out as super useful initially, but you can do really cool things. So for example, you now know that the exact same code that the server is using for its TCP IP stack is going to be running in the browser. So you can actually build some really cool debug tools where maybe you capture all the TCP traffic that's coming into the server, and then you go ahead and you replay that in the browser, and you want to do a debug, and you want to see actually what exactly was going on with each packet. And you know that it's the same code, whereas say you were doing that with Linux kernel, you would actually have to re-implement the TCP, enough of the TCP IP stack in the browser, and then hope that you got most of the similarities close enough that it actually did work. And then for those of you who are familiar with Flow or TypeScript, it's kind of like that as far as the type story goes, but it's much, much better, and it just works out of the box. So you get kind of type-safe code that works on the back end and front end. Third deploy target is mobile. So we can compile down to ARM64. And due to the history of OCaml, one of its strong points is very, very easy interop with C, Objective-C with foreign function interfaces, that kind of thing. So we can very easily compile down to, for example, a iOS application, and then make use of all of the native libraries that are available on there. And then finally, we have Raspberry Pi as an example. So again, we're compiled down to ARM64. And in this case, actually, the performance and size characteristics of the compiler output are really important. Raspberry Pis get better and better every time they're released, I guess. But there's still not a whole lot of margin there to play around with. So actually, it's quite important that we have something that is very efficient and is able to make good use of the resources that we actually do have. So as far as code reuse goes, it's kind of cool, where literally, we can have all the way down, just above the hypervisor, to the mobile, to browser, and to embedded devices, where we can actually share a significant amount of code, both type-safe and memory-safe, and we can make sure that it works across all these different targets. So correctness is a big thing in the ML world. I really like it because I work in Clojure quite a bit, and this is kind of the bane of my existence, is a null pointer exception is very, very painful to track down. Or in JavaScript, you have the undefined is not a function, which I think everyone loves seeing that in a stack trace. Line 0, undefined is not a function. So actually, just by the nature of construction in OCaml, this just doesn't happen. Unless you're doing some significant kind of foreign function interface within pure OCaml code, you are forced at compile time to deal with this. So you actually get this kind of very warm, fuzzy feeling about how correct your program might be. And as an example of that, here is the Fibonacci sequence in Emacs. And literally, as soon as I hit save, it tells me, hey, there's an error here. You're using a string when you have to use a number. And this is a silly example. But actually, if you think about it, all the way, literally, if I was working in the backend and the backend actually shared some code with the client. If I made a change in the backend and I hit save, it would immediately tell me if I had broken anything on the front end, which is really, really hard to do, generally speaking, with any other kind of setup, to get that both that immediate feedback and that sense of correctness. As far as performance goes, like I'll just say, generally speaking, it's quite good. It's used for high-frequency trading, like HFT and whatnot, and those guys care a lot more about performance than I generally do. So it's very good. OCaml is used by Facebook, Docker, Jane Street, so like a lot of these companies that put a lot of very serious projects in it. So who here has used Flow for JavaScript? All right, few people. Any of you contributed to it? It's pretty easy. It's some OCaml. It's not bad. Hip-hop VM, Docker recently used it. So Docker actually, Docker for Mac, took the pure OCaml implementation of the TCP IP stack and whatnot, and actually used that as a way of communicating between the container and the host environment. And because it was so easy and so modular to do, they were able to actually ship that very, very quickly. It's a very, very impressive piece of work. If you look in the credits for Docker for Mac, there is OCaml everywhere. So kind of revisiting the app dev goals that we talked about in the beginning, I feel like OCaml hits security pretty well. There is a whole class of memory issues, memory security vulnerabilities, which is obviated. There is a significant amount or less amounts of code, which means that the surface area is also significantly smaller. And then the type system also gives you some bit of security, I think, in terms of making sure that you're not passing around bad data necessarily everywhere. But there, you still have to think about it. But it's nice that there are entire classes of vulnerabilities that we don't have to worry about. So as human beings, we can kind of spend our limited cognitive powers focusing on a much smaller kind of domain. Correctness, again, it does quite a good job there. App performance, other people do a much better job of making sure that this works, but it works very, very well for us. The code reuse, like I said, I think is actually significant compared to kind of any other environment that I've worked with before. And then all this kind of goes towards maintainability because of the correctness, because the ability to change something in the back end or the front end and know immediately if I've broken anyone else or any other project. And then all of this kind of adds up to delivery speed. So whenever we hack on OCaml, it does tend to significantly go faster, especially after an initial warm-up period. And I say that as someone who really, really loves Clojure and who desperately misses a REPL whenever something goes wrong. So quick caveats. Like I said, a few bad things. So tooling and namespacing and whatnot in OCaml are nightmares. It can be really, really bad. Give you a quick example. I was working on my blog, and I had a function or a file named site dispatch, and I thought that was a little bit long. So I changed it to dispatch, and actually someone else in my transitive dependencies also had a file named dispatch, and then the compiler blew up. So it's not very pleasant, but actually this will be fixed in an upcoming release, hopefully. So they're working on namespacing and whatnot. OCaml, especially recently, has been moving really, really quickly. There's really cool stuff like effect handlers coming out. They changed their metaprogramming syntax. They have a new intermediate optimization that they call F-lambda. And so what ends up happening is, as a language, OCaml is moving quite quickly, and it can be hard for the learning resources to catch up. And so it's very difficult to kind of pick up on your own oftentimes. And then for some people, the syntax can be off-putting. I showed you a very nice slide of it, but it does get pretty hairy at times. And then, as with any other language, I'm sure you guys will be familiar with this, the community is smaller, and then this translates into libraries that are not available. To some degree, this is offset with the ability to interop, but overall, there are challenges of, like, in any other functional language, like it is challenging to actually get a community of significant size. And then the errors can be inscrutable. So, having said all of this, and it's single core, but we don't really care. They have multi-core coming out now. All this stuff is actually being kind of taken care of. So, in particular, Facebook has been investing very, very heavily in OCaml. So they use Flow, and they use, they build OCaml or Flow with OCaml. They build Hip-Hop VM with OCaml. The original version of, or the original prototype of React was prototyped in SML. So there's like a very strong investment at Facebook in ML generally, but OCaml specifically. So for how many of you guys have heard of Reason? All right. It's kind of a confusing thing. I think if you were to just look at the docs as is, it's not totally obvious kind of what the use is and why it exists. But basically, it's a meta language on top of OCaml. It's the same compiler. It's the same language and whatnot. They're not forking it. And basically, its main goal is to rework the syntax to make the syntax more approachable and to make it so that we can separate syntax from semantics, which is a really interesting idea, where we can actually divest some of the concerns over like bike shedding syntax, because everyone feels opinionated about syntax. Very few people feel qualified to give meaningful comments on, for example, effect handlers. So they're doing a great job of actually splitting those two things out and saying, you can have the syntax that you want, and then we're going to focus on just the semantics. They also encourage like a very blessed stack, so they kind of pick the tools just out of the gate. This should work for you. And they focus really, really heavily on developer experiences. So you'll see kind of some touches from Elm and some other things. So an example, here is an error that you might get from OCaml if you use the wrong type. So you can see all the information is there, right? So like it's line 8, character 5. It was a type string, but it wanted a type bool. Like what more do you really want, right? And for like before Elm, everyone was like, this is it. This is great. But they work on better errors for Reason, and so you get this kind of error, where it literally kind of tells you exactly where the error happened, what it was, and what it wanted. And they actually go a step further, where they kind of they embed kind of like a robotic pair buddy in some ways, where, for example, in this case, you get a warning that an optional argument can't be erased. And this has this kind of a specific meaning in OCaml, but if you were just beginning out, like it wouldn't be obvious why this is important or what this means or how you fix it. And so they do a good job of actually saying, this is kind of very Elm-ish, right, where we can bring OCaml into the modern age, call it, where they give you an explanation of where the error happens, why it happened, and why it's important. So super cool stuff happening with Reason, where if you didn't like OCaml back in university, and if you didn't like it before, then you might want to give it a try now. So if we look at actually the syntax of it, on the left-hand side, we have JavaScript, and on the right-hand side, we have Reason. It's really hard to tell them apart, generally speaking. I think Reason just looks slightly better. And that's just about it. Like overall, they're pretty much the same. So again, like we write this, but we get the ability to actually write systems-level code. We get the ability to write for native mobile. We get the ability to share across all the different devices. This is another example. Again, just more succinct. So you get pattern matching in the language as a first-class concept, etc. So this was I wanted to show you an ugly OCaml, and that's about as ugly as it gets. I wouldn't, like if you can stand that, then I think you're going to be all right. So just a quick thing, shout out to Edgar. So he's done a lot of work on the iOS OCaml setup to make it so that it's actually very, very smooth. So you can be running an an iOS app within a few commands. And then Daniel, the precursor guy, has been super helpful for, I think in particular in the functional community, Clojure and ML languages stand on opposite sides of a very great chasm. And it's really nice to have someone to kind of bounce off ideas. So, and then thanks to my company for allowing me to come out here. Cool. Any questions?
Tell us about your experience with the OCaml garbage collector. Is it great? Are there pain points? Or what's going on?
So the OCaml garbage collector is very famous for being a very capable and very, very high allocation rates garbage collector. And it's really good for certain domains. Generally speaking, for the vast majority of applications that I think we would be working on, it's really, really well suited. It works very well. There are cases, for example, with animation on mobile, where you are about to launch into an animation and you cannot afford to skip a frame. You cannot afford to incur that GC pause. And it would be really nice to be able to sell the garbage collector in a very intuitive way. Say, hold on, I know what I'm doing. Give me a couple of seconds to finish this animation. That's not really there as of yet. There are definitely ways to work around it. But generally speaking, for the vast majority of applications, it's very, very good. Certainly, I would say, in my experience, it has been considerably better than the JVM garbage collector for a lot of our domains.
For the compile to JavaScript version, how big is the overhead for sort of runtime, standard library, and other optimizations like that code elimination or stuff like that?
Sure. So I work with ClojureScript quite a bit, and it's night and day. It is a very, very small binary that comes out to the other side. It is not amenable to, for example, the Google Clojure dead code eliminator right now. There's actually a PR for OCaml itself to do a dead code elimination at the bytecode stage. So we would actually just skip the entire, the JavaScript that was output would be just specifically what you wanted, and we wouldn't have to worry about that. That said, it's already quite small. Although, like I said, because you can compile basically any pure OCaml, there are some very big libraries. And if you accidentally pull in something, you'll get a 20 megabyte JavaScript file. But generally, you see that, and then you take that out. Yeah, so it's very small. It's good for either mobile or for browser. Cool. We good? All right. All right. Thank you.